Welcome back. Today we are going through lesson 11.6, which is all about combinations. And as part of that, we're going to talk about the binomial theorem. So in our previous lesson, we talked about permutations. So this is kind of the next step of that. So combinations are arranging a set of objects in which the order does not matter. So if you remember the permutations, order mattered, what place people finished or whatever. In this case, the order doesn't matter. So it changes the way we're going to calculate things a little bit. So let's look at a few examples of this. In example 1, we have 4 people that we're going to be talking about in these examples. Alice, so we're going to use A for that. Benjamin is B, Carla is C, and Dante is D. So part A says if the 4 people compete in a swimming competition, how many ways can first place and second place medals be awarded? So when we think about this, if Alice finishes first and Benjamin finishes second, that's different because the place matters than Benjamin finishing first and Alice finishing second. So those are 2 different things that are happening there. So in that case, the order does matter. So we can do that with everybody. So maybe Alice finishes first and Carla finishes second, or vice versa. Or Alice could finish first and Dante could finish second, or vice versa. So we go through all the possible ways that first and second place can be finished. And then the last one involves Carla and Dante. So those are all the possible ways. So when we look at it that way, when we're talking about a first place and a second place medal that's happening, there are 12 different ways that people could finish in those 2 spots. B is looking at it a little bit differently. So if the 4 people that we're talking about organize a fundraiser, it's asking how many ways can 2 people collect them or be selected to collect the money. So 2 people are going to be in charge of collecting the money. In this case, those same combinations can happen again. So those same combinations can happen again, but this time, if Alice and Benjamin are collecting the money, that's the same thing as Benjamin and Alice collecting money. So those options that we came up with up above, those are all the same 2 people doing the job now. So each of these columns here, we wouldn't care about the repeat because they're just collecting money. It doesn't matter which order they're collecting the money in. So if we think about that, we really only care about one of the rows, and so it would only be 6 ways to collect that, right? So when the order doesn't matter, it changes how we're calculating how many different ways things can happen. So if you remember from permutations, we have a formula that we can use to help us determine those ways without having to write them all out, like we just did in this example. So that formula looks like this. So this should look somewhat familiar again. So this is the combinations formula. So we write it as NCR. The C is a big letter, and then the N and the R are subscripts on the side. So remember, N is the total number of objects. And R is how many we're selecting. So the formula for a combination is n factorial, which remember means n times all the numbers below it up to 1, divided by n minus r factorial times r factorial. So that denominator is helping divide out the repeats. So when we talked about Alice and Benjamin before being repeats, same idea here. And then we just want to remember that if we have a total of n objects and we're selecting all of them, there's only one way that can happen for a combination. All right, so let's look at some examples here. So the first one says create a formula for the problem in 1b. So going back to Alice and Benjamin and their friends collecting money, remember that we had 4 people to choose from, and we were going to choose 2 of them. So if I plug those into the formula, I have 4 people to choose from on the top, so 4 factorial, divided by 4 minus 2 factorial times 2 factorial. So when I simplify that, I get a total of 6 ways, which we know from before was the correct answer. Okay, so let's look at another one. So this time we have 9 objects and we're going to choose 6 of them with order not mattering. So that's going to be 9 factorial over 9 minus 6 factorial times 6 factorial. So when we simplify that out, or when we think about it, we have 9 times 8 times 7 times 6 factorial. So just abbreviating it rather than writing out 6 times 5 times 4 times 3 times 2 times 1. And then on the bottom, we have 9 minus 6 is 3. So that would be 3 factorial times 6 factorial. So when we write it that way, we can see that the 6 factorials cancel each other out. And we're left with 9 times 8 times 7 over 3 times 2 times 1. And that simplifies out to a total of 84 ways to choose 6 items from 9. All right, and then this time we have 12 items we're choosing from, and we just get to pick one of them. So the formula would look like 12 factorial over 12 minus 1 factorial times 1 factorial. All right, so again, kind of shortcutting it here. That would be 12 factorial over 11 factorial times 1 factorial. So 12 factorial is 12 times 11 factorial over 11 factorial times 1 factorial. So those 11 factorials cancel out. We're really just left with 12 over 1, which is 12. So those are some basic combination problems. Now we're going to use that to solve some word problems. Okay, so in example 3 here, we're going to write the combination out and then use it to solve the problem. So a team has 18 softball players. So we have 18 total players that we're going to choose from. And it says, how many ways can 2 players be chosen to refill the water cooler? So that is what my combination would look like. 18 choose 2. So that would be 18 factorial over 18 minus 2 factorial times 2 factorial. So again, simplifying that out, I'd have 18 times 17 times 16 factorial, because on the bottom, when I do the 18 minus 2, that's 16 factorial times 2 factorial. So the 16 factorials cancel each other out. We're left with 18 times 17 over 2 times 1, which would be 153 ways we could choose 2 players out of the 18 to go refill that cooler. All right, looking at the next one. This time we have a group of 40 people, so that's our total, who are going to go run a race. We want to know how many ways can the top 7 finishers be awarded. So we are choosing 7 top finishers to give prizes to, or to advance to the finals. All right, so when we set up our combination, we've got 40 factorial over 40 minus 7 factorial times 7 factorial. So when I write that out, we have to go 40 all the way down 7 spots to 33. And then again, that 40 minus 7 would be 33 factorial over 7 factorial, which is 7 times all the numbers below it. So those 33 factorials cancel out. When you multiply the numerator and then divide by the denominator, it's a total of 18,643,560 ways. So again, that's the number of ways 7 different people out of the 40 could finish in order to advance to the finals. All right, let's look at C here. So this time we have 16 applicants, and we are going to select people for 3 different job positions that we have available. So the formula for that would be 16 factorial over 16 minus 3 factorial times 3 factorial. So 16 times 15 times 14 times 13 factorial over 13 factorial times 3 factorial. Cancel things out. When we divide that out, it comes out to 560 different ways to select 3 people for those jobs. Okay, so we're going to take this now one step further and look at something called the binomial theorem. So we are going to use something called Pascal's triangle to help us in determining these things in a slightly different way. So Pascal's triangle is a triangular array of the binomial coefficients. So think about binomials, those are 2 terms. The coefficients when you're multiplying them out. And we find the triangle by adding the numbers above it. So you can see the binomial theorem written out over here. And we use this because the combinations are what determine the coefficients on our expansions of binomials being multiplied together. So here's kind of what it looks like. So Pascal's triangle, like it says, is formed by taking the sum of the numbers above it. So in this case, let me get a different color here. So we start, if we have x plus y, that's our binomial, multiplied to the 0 power. Anything to the 0 power is 1. So that is just that one. If we have x plus y to the first, remember that would result in just x plus y. Anything to the first power is itself. So the coefficients there are 1x and 1y. So then what we do is we take that one step further. Now we're going to square it out. So remember, hopefully, if we have x plus y squared, that's x plus y times x plus y. That comes out to x squared plus 2xy plus y squared. So the coefficients there go 1, then 2 on xy, and then 1 on y squared. So continuing that pattern down, if we use it to add the numbers above it, right? So the 1 plus 2 and the 2 plus 1, when we take that all apart, the next row of Pascal's triangle is 1, 3, 3, 1. So when we multiply x plus y by itself 3 times, the coefficients on our terms are 1x to the third, 3xy squared, or sorry, 3x squared y, then 3xy squared, and then 1y squared. So this idea helps us formulate the coefficients without actually having to multiply it all the way out. All right, so let's look at the next one. So when we multiply it out to the 4th power, the coefficients, when we add the numbers above it, come out to 1, 4, 6, 4, and 1. So this is a 4th degree, so it would be 1x to the 4th plus 4x cubed y plus 6x squared y squared plus 4xy cubed, and then plus 1y to the 4th power. So it's a shortcut to multiplying those out. All right, for this next row that we have, again, adding the numbers above it, the 1 and the 4 and the 6, so on and so forth. The next row of Pascal's triangle is 1, 5, 10, 10, 5, 1. So we can see those coefficients 1, 5, 10, 10, 5, 1. And then Pascal's triangle continues for as long as we need it to, but for our purposes, we're going to stop at the 6th power. So you can see the coefficients then would be 1, 6, 15, 20, and then back down 15, 6, and 1. All right, so here's how we're going to use Pascal's triangle to help us. So the triangle can be used to calculate combinations. So for any given combination of n choose r items, n is the row of the triangle. So that tells us how far to go down. And then r is the r plus 1 element in that row. So you go one step further basically than how many you're trying to find. All right, so we're going to kind of flip back and forth to the triangle that we were just working on. So this one says to choose 2 items from 4. So what that means, based on what we were learning above, is that we are going to go to the 4th row, and then we're going to choose the term that is one past how many we're choosing. So we were choosing 2 items out of 4, so I'm going to go to the 3rd item in that row. So remember, that is because we were choosing 2 out of 4, we go one further than that. So if we go back to our triangle and look, in the 4th row, the 3rd number over is 6. So there are 6 ways to choose 2 items from a total of 4. So you may want to pause the video here and try B on your own. For this one, we're going to go to the 6th row. And then if we go one further than 3, that puts me at the 4th item or element in that row. So 6th row down, 4th element over would be 20 ways to choose 3 items from 6. So to sum this all up here, the coefficients in Pascal's triangle are symmetrical, and they follow whatever row of the triangle we need for the total number of items that we're choosing from. So the total number of terms is n plus 1. The exponent of x in the first term and y in the last term. So if you looked at those, it always started with an x to some power and it ended with a y to some power. That's always going to be to the nth power. And then what happens as we move across our answer, the exponent of x is always decreasing by 1 from left to right. So if we started with x to the 4th, then in the next term it would be x to the 3rd, so on and so forth. And the exponent of y is doing the opposite. It's increasing by 1 from left to right. So the first term is just x squared. There are no y's. Then the second term is going to have y to the 1st power, and it keeps going up until we reach n. And then we also should see that the sum of each of the exponents in each term totals up to n. So when we're in those middle terms, if we have x to the 4th to start, then y in the next term is going to add up to 4 with the x. So x to the 4th, x to the 3rd, y to the 1st, so that we still have a total of 4 in the exponents. All right, so we're going to use all that information to do some expansions here. So the total number of terms is going to be n plus 1. So in this case, our total number of terms is going to be 1 more than 6. So we're going to have 7 terms to write out here. So it's kind of a lot. So when we write out our polynomial, it always starts with a to the highest power. So that would be a to the 6th. And then we're going to add to it, since we're on the 6th row, so we're using the 6th row of Pascal's triangle here for the coefficients. The next coefficient is 6. My a power goes down by 1. My b power goes up by 1. So it would be b to the 1st, or just b you can write. Then again, using Pascal's triangle, the 3rd coefficient is 15. Now I'm going down 1 power for a, up 1 power for b. And then we keep going. The next coefficient is 20. Down 1 power on a, up 1 power on b. And now that they're equal, we start going back down on Pascal's triangle. So the next coefficient is 15 again. Down 1 power on a, up 1 power on b. Next coefficient is 6. Now we're down to just a and b to the 5th. And then we finish off with just the b's to the 6th power. So that would be the entire thing. And again, remember that these coefficients that are happening out in front, the reason we're talking about this right now is because those coefficients are coming from a combination. So in this case of like the 15, let's say, that is coming from a combination. of 6, choose 2. 20 is coming from a combination of 6, choose 3. So that's where Pascal's triangle and combinations come together. All right, let's do 2 more here. So for this one, we're raised to the 3rd power. So I'm going to look at that row on Pascal's triangle, the 3rd row. And I know if we look back that the coefficients are 1, 3, 3, 1. Now what happens in this one though is that we have a 2x here, so we kind of have to keep that in mind as we go. So what that means is that my coefficient is 1, but 2x, the whole thing, is being raised to the 3rd power. So we're going to have to simplify that a little bit here in a second. Then my next coefficient is 3, and then 2x is being raised to the 2nd power, and y would be raised to the 1st. And if we keep going, my next coefficient is 3. Now 2x is only being raised to the 1st power, and y is being squared. And then finally, we just have y to the 3rd. So that's what it would look like. We're going to simplify a little bit though. So when we do 2x cubed, 2 cubed is 8. So 2 to the 3rd power here is 8 times the 1 we already had out there is 8. And then x to the 3rd power is just x to the 3rd power. So that simplifies to 8x to the 3rd, even though the original coefficient from Pascal's triangle was 1. Same thing here, 2 squared is 4. So that's 4 times the 3 that was already out there. That's 12x squared. And then our 3rd term here, 2 to the 1st power is just 2. So 2 times the 3 that's out front, that's 6xy squared. And then we just have the y cubed. So that would be my final answer for that one once I simplify the coefficients with the term that was being squared or cubed. All right, so for this one, our first term is 3m, and our second term in the binomial is 4n. So we're going to write it all out, but then we'll have to simplify a little bit again. So our coefficients on the 4th row are 1, 4, 6, 4, 1. So I'm going to say 1 times 3m to the 4th power. And then we have 4 for our next coefficient. 3m is now going to be to the 3rd power because we're going down 1 on that one. 4n is going to be to the 1st power. Next coefficient 6. 3m is going to be raised to the 2nd power now. 4n is also going to be raised to the 2nd power now. Then our next coefficient is 4. 3m to the 1st, 4n to the 3rd, and then finally we end with 1 times 4n to the 4th. So that's what it looks written out. Now we are going to simplify. So when I do 3 to the 4th power here, it's 81. So I have 81m to the 4th. 3 cubed is 27 times 4. And you have to remember that that's also being multiplied by this 4 and the 4 on that guy. So we're actually multiplying 4 times 27 times 4 again. That comes out to 432. We've got m to the 3rd power, n to the 1st. All right, next term, 3 squared, that's 9, times the 6 out in front, and then times the 4 squared, which would be 16. That gives us a total of 864. M to the 2nd, n to the 2nd. Now we've got just 4 times 3, and then times 4 cubed. When I multiply that all the way out, I get 768. M and n to the 3rd. And finally, we have 4 to the 4th power, which is 256, n to the 4th power. So that is how we use Pascal's triangle to write out some binomial expansions that are going on. All right, we'll see you next time.